Back here, this is going to be our final video for exponential decay here in Module 6. So let's take a look at what we've got. According to the International Basketball Association, or FIBA, I don't know where the F comes from, a basketball must be inflated to a pressure such that when it is dropped from a height of 1,800 millimeters, it will rebound to a height of 1,300 millimeters. Maddie decides to test the rebound ability of her new basketball. She assumes that the ratio of each rebound height to the previous rebound height remains the same at 1,300 over 1,800. Let f of n be the height of the basketball after n bounces. Complete the chart below to reflect the heights Maddie expects to measure. Okay, so each time we're going to multiply by this, okay, because this is the ratio that we want, right? So the previous height to the next height, we're going to multiply by that 1,300 over 1,800. Okay, so in this case, we're going to get exactly 1,300, right, after that first bounce, which is exactly what we're supposed to get. It will rebound to a height of 1,300. For the next one, we'll multiply again, and I'll just do this in a calculator here. Okay, and we get 938.89 millimeters, we'll say. We'll round to 2 decimal places there. Okay, do it again. Okay, and we get 678.08, and do it one more time. And we get 489.72, approximately there. Again, milliliters. Okay, which makes sense because each time the ball rebounds, right, it's going to not go as high as before. Okay. Write the explicit formula for the sequence that models the height of Maddie's basketball after any number of bounces. So again, we're talking about growth or decay here. Is the height of the basketball growing or decaying? Decaying, right? The bounce is getting smaller. So again, amount equals, and our principal, our starting amount here is 1,800. And then it's 1 minus, and then what is our fraction here? What are we decaying by every time? Okay, well, here we're multiplying by this every time, okay? We're not given a percent change here, right? We just have this ratio. But remember, this is what we actually multiplied by every time here. So we're not going to need to worry about this 1 minus stuff. We already know the exact number that we're multiplying by every time. It's 1,300 over 1,800, which if you want to, you can simplify to just be 13 over 18. Okay, it's really your choice there. And of course, then to the t, or the n, if you want to say the number of times it bounces or anything like that. Okay, so now we're supposed to plot these points from the table and then connect the points with a smooth curve and use the curve to estimate the bounce number at which the rebound height will drop below 200 millimeters. Of course, we could also solve for this too, but let's go ahead and use the graph. Okay, so number of bounces, well, again, at 0 it was 1,800. 1, it's 1,300. So that's halfway between there. Okay, 2, it's 938.89. So 900 and then 38 would be like a little bit right there. 3 will 678. So that's gonna be like right here. 4 is 489. So I know something like that right there. Okay, and so we'll connect these dots as carefully as we can here. Just going to probably do something like this. Okay. So then where would it drop below 200? Wow, it actually kind of crossed really nicely. There's 200, right? And it's right here after about 7 bounces. Okay, is what we would expect it to be below 200 millimeters then. Okay. So let's go ahead and solve this actually just to see if we're close. So we'll plug 200. I'm going to do it over here. Plug 200 in for A equals 1,800 times, and again, I'm going to go ahead and just simplify that to be 13 over 18 to the n. So divide both sides by 1,800. Okay, this fraction actually simplifies to just 1/9. Okay, use a logarithm. So I'll just use like log base 10 here on both sides. Okay, and so then that n can come out front. And we'll divide both sides then by the log of 13 over 18. So those cancel. We have n is exactly the log of 1/9 over the log of 13 over 18, which is approximately 6.75. So 7 bounces, right? Because that's what it would take to get to the actual, 200 milliliters there. Okay, so pretty close. So in summary, here is another way of writing that formula. F equals A times B to the T, where again, A is that initial amount, and then that B is the 1 minus R, or 1 plus R, depending on growth or decay. Or that's decay. Okay, that becomes the B. And of course, T is still time. Okay? So there we go. Thanks, guys, and we'll catch you later.